fundamentals. So now we have understood how the things are going to happen in the case of linear regression model with one variable. Now, in practice, if you try to see whenever you are trying to conduct the experiments, usually you will have more than one variables. They are going to affect the outcome. For example, you can say agricultural experiment. The yield is going to be affected by several variables like as quantity of fertilizer, rainfall, temperature, etc. So now we are going to extend the simple linear regression model to a more realistic model, which is actually the multiple linear regression model, right? So now you will see here that this is that we are simply going to extend the concept of univariate in a multivariate setup. So you have to be very careful, because when you are trying to go for multivariate setup, then there are also interactions also. Right. So now we will take here the same example which I took in the last lecture. And now we will try to see what happens to this model. Earlier, we had taken only one variable and we had understood that how we are going to do the regression modeling. But now we will try to take here all the three variables and we will try to see that how we can do the modeling and how are we going to interpret the results. And in this case, actually, you will get the outcome of the software which I showed you earlier. And then we have to understand that how are we going to interpret those things. So obviously, whenever we are trying to consider the regression modeling with a dependent variable and more than one independent variable, this is called as multiple linear regression model that we have understood. So now what will happen, as you have seen that expected value of y earlier was beta 0 plus beta 1x, but now it can allow you to consider more than one independent variable at the same time. And yeah, and then now the thing is this, earlier you assumed that the relationship between y and x is linear. But now if you are trying to go through to a multi-dimensional space, you can think, well, if you try to take 2-dimension, I can say that is going to be an area, 3-dimension possibly, some flat surface, but beyond 3, 4, 5, 6 direction, it is very difficult to assume that what will be the real structure. But at least conceptually and theoretically, we can safely assume that the joint relationship of all the independent variable with the dependent variable is normal. Right. Okay. So now we have to first formulate the model. So now what I'm doing to do here, that earlier we had expressed the model as y is equal to beta 0 plus beta 1x plus epsilon. So now I will try to extend this beta 1x as beta 1x1 plus beta 2x2 plus beta k xk. And well, in case if you want to have an interceptum in the model or not, for that you simply have to see that if you try to look in the first variable x1. So if you try to make all the values of x1 to be 1, then you are going to have here an interceptum. So that is why this is the structure in which we try to consider the multiple linear regression model in the most general framework. And whenever we want the intercept term to be there, I can just make the first value of the observations to be just 1. That's all. So here now we have here k independent variables x1, x2, xk, and we have here k regression coefficients which are associated with each of these x1, x2, xk. Right, so this is the multiple linear regression model. And now if you try to see here, what is here beta 1, beta 2, beta k, they are called the regression coefficients which are associated with x1, x2, xk respectively. And epsilon is the random error component that is trying to show you give you an idea about the randomness involved in the experiment and in the model. Right, so there is no issue that now means earlier you had assumed the epsilon is trying to capture all those effects which you cannot handle. Similarly, in the case of multiple linear regression model, this is the same concept. And now means it will also take care of other factors also, that there are some variables which you want to include in the model, but because of any reason you are unable to do it. So this epsilon is going to help us. Right. And now what about the interpretation? Means if you assume that the random error in the population on an average that is going to be 0, then the jth regression coefficient beta j can be expressed as the partial derivative of expected value of y, that is the average value of y with respect to xj. That means beta j is trying to indicate the increase in the average value of y with an increase of 1 unit value in the gth independent variable. So for example, if I say my model is y is equal to 3 plus 4x plus 4x1 plus 5x2. So 4 and 5, they are the regression coefficient associated with the x1 and x2. So that is going to indicate that if you try to make 1 unit change in the value of x1, then you are going to get say this 4 unit of change in the average value of y. And if you are trying to make the change of 1 unit in the value of x2, then you are going to make a change of 5 units in the average value of y. Right. Now, in this case, so what you try to do, as we had considered the observations, say xi, yi, in the case of simple linear regression model, similarly, you can also consider here the multiple linear regression setup. And suppose, for example, if you try to see in the last column of this explanatory variable, so we are going to conduct the experiment. For example, if I have k variables, I am going to assign them certain input values. And then based on that, I am going to observe the first value here, y1. For example, I can take here 20 centimeters of irrigation, 2 kg of fertilizer, 30 degree of temperature, and then I try to obtain the first value, y1. And then similarly, we try to repeat it, and I try to take a different value of quantity of fertilizer, temperature, irrigation, and then we try to obtain the value of y2. So in this process, my simple suggestion is that whenever you are trying to conduct the experiment, try to choose the values of the independent variable in such a way so that they are trying to reflect the entire cross section of your data set. Right, if your variable takes negative value also, then you try to take some values, conduct the experiment with some negative values, some positive values, and so on. So now we have here the observations in this format. Right, so all the x1, x2, xk, they are going to be my input variables, and y is the output variable on which we have obtained the data. Now, if you try to see here, if you try to look at this example, what are your here these values? If you try to compare this x11, x12, x1k, they are simply your here this value here of x134 in the first observation, that is your first observation on x1, then x2 equal to 3 is the first observation on x2, and x3 equal to 15 is the first observation on x3, and then based on that we have obtained here the value of y, and so on. We have repeated this experiment say 20 times, and we have here 20 values. Now, if you try to see, I can represent all these values here in the form of a matrix. You can see here all these values which are in the columns of y here, that is going to create one column vector, and all these values x1, x2, x3, they are going to create another matrix here like this one. So you can compare here that I am writing these values of x and y in the form of vectors and matrices. Right. And now, why I'm trying to do it? Because if you try to see, as you assume in the case of univariate, that each pair of observation xi, yi, that is also going to follow the simple linear regression model. So similarly, we can assume here also that when we have this observations on k independent variables and then observation on y, then all these observations are also going to satisfy the linear equation or the multiple linear regression model. And so this is what I have written here, y1, y2, yn in the format of the model. And now these are an equation, so I'm simply trying to express them in the form of a vectors and matrices. That is very straightforward for you all. And this here, so now here this y here is the n cross 1 vector of the observation on the response variable, x is the n cross k matrix on the observations on independent variable, beta is the k cross 1 vector of regression coefficients, and epsilon is the n cross 1 vector of random error components. And if you try to see here, this is what I have written here. Y is a 20 cross vector, a 20 cross 1 vector of the observation, x is a to 20 by 3 matrix of the observations on the independent variable. And if you want to have here an intercept term here, for example, here before this first column, you can add here one column with all the values to be here 1, 1, 1, 1, 1. Right. So now you have here this model y equal to x beta plus epsilon. Right. So where now we have transformed this univariate equation into the setup of a multivariate equation. That doesn't make any difference actually, but you know that whenever we are trying to handle the multivariate setup, if you can transform your quantities in the form of vectors and matrices, then the life becomes simpler. Okay. So now we have this setup, and yeah, I'm simply trying to show you here that if you want to have here the intercept term in the model, you can just add here one column vector of 1, 1, 1. But here you have to be very careful, because whenever we are trying to find out different types of results, they are based on some number of observations and some number of independent variables. So you have to be careful here whether you are trying to take the number of variables to be here k or say k minus 1. If you remember, means earlier in this matrix we have here k independent variable x1, x2, xk. But now if you try to see here, means if you try to take here x1, x2, xk, then the total number of independent variables in this matrix, they are going to be actually here k plus 1. So if so, you have two options. Either you work with k plus 1, or you try to simply assume that the number of independent variables are only here k minus 1, and 1 here is the column vector of the intercept term. So the total number of independent variables becomes here only k. And yeah, this first column, this is also a value of an independent variable, which always takes the value 1, where you don't have to do anything. Right, okay, so now we are coming more formally into the structure of multiple linear regression model. So there are certain basic assumptions, and they have to be satisfied if you want to use the software or you want to interpret the results correctly. So if you try to interpret these assumptions, actually these are not assumptions. The fact is this: when we are trying to do our statistical analysis, well, that is also a sort of algebra mathematics. So we have to make certain assumptions so that we can make our algebra manageable. Otherwise, sometimes the algebra becomes too complicated and we are unable to get any outcome of that one. So we try to make some assumptions which are mathematical in nature, but usually they have some interpretation also. So if you try to see here, the first assumption I'm writing here, that is expected value of epsilon is equal to 0. So as I said, expected means the mean. So you are simply trying to assume that the mean of all the random errors is 0. That is not a very bad option, because if I simply had it been a live class when you are sitting before me, means if I simply ask the age of all the participants. So somebody age maybe 25 years, but he or she might tell us 26 years or 24 years. So what will happen that every value will have some random error in terms of positive or negative. So when you are trying to take the average of such a large number of values, then you expect that on an average the value will come out to be close to 0. And the next assumption is expected value of epsilon transpose is equal to sigma square in. Actually, that is only the covariance matrix of this random error. So you are trying to assume here that the covariance matrix is in the form of sigma square into identity matrix. So identity matrix, you know that all the values are on the diagonal are 1 and off diagonal elements are 0. So when you are trying to say this covariance matrix is in the form of sigma square in, that means all the variances which are on the diagonal element, they are just sigma square. They are just constant. So you are assuming that the variability across the observation remains the constant. And that is not a bad option, because when you are trying to consider an experiment, say inside a lab, then the temperature, moisture, the level of fluctuations, etc., in any mechanical equipment, they will almost remain the same. Either you are trying to conduct the experiment today or day after tomorrow. So from that point of view, we can very easily assume this variance to be sigma square. And the off diagonal terms are 0. This means all the random errors, they are independent of each other. That is also a valid assumption. For example, if today there was some more humidity in the in your lab under which you obtain the observation, it is not necessary that next day if you come, the same level of humidity is going to be there. That is going to change, right? So it doesn't make any sense to assume that the humidities of today, they are going to affect tomorrow. Well, I'm not saying that these things are not possible. Well, in practice, these violations are there. It means even I can give you the violations of these two assumptions. For example, if you are saying that the variance remain constant, this can also be violated. How? I can give you a very simple example. Suppose my salary is 10,000 rupees a month. And if you try to analyze the type of food I have, so possibly I can have one vegetable, one chapati, but suppose my salary becomes 20,000. So now there will be more variation in the food, right? You can have here two types of vegetables and some more type of say dal or something like this. And as the my salary is increasing, the variation in my food consumption will be changing. And possibly if my salary becomes more, possibly one day I may also go to the restaurant. And first I go to the restaurant for simple food, then there's exotic food, foreign food, etc., etc. In this case, you can say that the observations, the variability is increasing. Similarly, if I try to say that whether the variability is decreasing or not, so suppose I ask you to learn the typing. So now when you are trying to learn the typing, today you go for the typing test, possibly I give you one document, possibly you can make 100 typing mistakes, and I ask you that you practice. And suppose after 3 days, your number of mistakes will come down. And after that, if you practice more, your number of mistakes are coming down. That means as you are getting the observations, this variability is decreasing. So in the first case, the variability was increasing. Now the variability is decreasing. Similarly, for the independence of these random errors, for example, I take a very simple example. Suppose at my home, I know that the consumption of rice is 40 kgs a month. Now, I take the observation on the monthly consumption on the rice, or how much I have to buy from the market. Now, suppose towards in the last week of the month, I get here some guest, some friend, and I have to suppose buy 20 kg of rice more. Now, what do you expect? The purchase of rice in the next month, is it again going to be 40 kg, or that is going to be dependent on the previous month? If some rice is left, then we will try to adjust it. That means the observations are not independent. And for example, if you try to see the share market prices in the vegetable market, time series data, the observations are not independent. But anyway, we have tools when these violations are happening, then we have suitable tools for those things also. But at this moment, I'm assuming that the variance of the random errors, they will remain the same, and uh, and uh, and the random errors are going to be independent of each other. And if you try to see the structure of your model, this is here y equal to x beta plus epsilon. So you assume here that x is a non-stochastic matrix. That means x is fixed, it is not random. The interpretation of this is like, for example, if somebody is nowadays trying to conduct the clinical trial for the COVID vaccines. So now those clinical trials are happening somewhere in UK, USA, etc., and in India also. But those, but for example, considered in the news, uh, there was a news that now the India is ready for the production of the COVID vaccines, and they are going to be exported to other countries. Now the clinical trials have been made only in this country. Now that is being used in some other countries also. So we are trying to make here that the patients who participated, they are independent of uh, the reaction of the COVID vaccine. And the same reaction, what has been seen in Indian people, that will be there in Nepalis, Bhutanese, or any other people in this world. So that is the meaning of here. X follows a non-stochastic matrix. Now that now after fourth, I come to here third one. Third one I had not told specifically. This is that we are assuming that X is the full column rank matrix. That the rank of the matrix X is actually K. Actually, at this moment, I can give you here two aspects. That first is the mathematical aspect, because the way we had computed the beta 0 and beta 1 in the case of simple linear regression model, similarly, we are going to compute here the beta vector. So that you will see that will be depending on the inverse of a function of this matrix X. So for that, we will need this condition so that we can find the inverse of that matrix. For that, we will need here rank of X to be here K. From the application point of view, this rank of X equal to K means all the variables X1, X2, Xk, they are linearly independent. What is the meaning of linearly independent? For example, if I say, suppose I try to collect the data on three variables, the income, expenditure, and saving. Now, if you try to see, the income is going to be the same as expenditure plus saving. So in this case, the data is not going to be really linearly independent, but there exists a linear relationship. So now under this type of cases, you will see a couple of problems comes, and then we have to use appropriate tools to solve the problems. And now finally, in the fifth assumption, I'm trying to write down that epsilon follows a normal distribution or a multivariate normal distribution with mean vector 0 and covariance matrix sigma n square in. So these are the basic assumptions. So now the model of the story is very simple. Before you try to put your data into the software, first try to think whether these assumptions are getting valid or not. We have some statistical tool, we have some graphical tool, but besides those things, it is very important. You have to understand what they are trying to indicate to you, and then you have to see whether this is really happening in real life or not. Right. So right now I come to the aspect that how are we going to estimate the regression parameter beta. So earlier we had estimated beta 0 and beta 1, but now I'm trying to estimate the entire vector beta. So I try to use here the same concept principle of least square, or equivalently you can also use method of maximum likelihood. Both are going to give you the same outcome. Right. So the ordinary least square estimator, which is also said as OLS, that is ordinary least square estimator of this now vector beta. This is obtained here as a here B, which is equal to X transpose X whole inverse X transpose Y. Now, the next question comes here, can you estimate it? Now, if you try to see on the right-hand side of this equality sign, you know the observations on X, you know the observations on Y. So now this is only X transpose X, means you know how to multiply the two matrices, how to take the transpose, and then how to find out the inverse, and then you can multiply all these things together to get the value. Right. Now, if you try to see here in the structure of this B, this is here X transpose X whole inverse. So this unique inverse is going to be found only when rank of X is equal to K. And that is why we had made this assumption that X is a full column rank matrix from where you can take the help while finding out this ordinary least square estimator. Right. Okay. So now you can see your all the parameters beta 1, beta 2, beta p, they are going to be estimable from this quantity. The reason why I am trying to show you this mathematics is that sometimes in my experience, I have seen that people think that, okay, these things are arbitrary, these things are coming from the sky, and then they can use it blindly. But then I'm simply trying to show you that it is not correct. These things are based on some statistical tools, statistical concept, and that is how we are trying to use them. Right. Now, so we have now estimated the beta. Now, other quantity which we would like to estimate is the quantity sigma square. And then if you try to see here in this model here, y equal to x beta plus epsilon, now you are assuming x to be here fixed, beta to be here fixed. So epsilon is the only quantity on the right hand side which is random. So the variance of y is going to be the same as variance of random. So although you are assuming that epsilon has got a variance sigma square, but that is also indicating that the variance of y is also sigma square. So that is why we are interested in knowing that how much the variability my observation have. And obviously, when the variability is high, my modeling is going to be troublesome. The results are not going to be good. So we would like to be extremely watchful and careful here, right? So that is why we would like to know that what is the value of variance on the basis of given sample of data. Why? Because you see, the sigma square is the value of the variance in the whole population. That is not in the sample. And that is unknown to us. So we want to know its value on the basis of the sample of data. And this is how we are going to estimate it. Y minus y is known to you, x is known to you, and b you already have obtained here. So that is going to be 1 upon n minus k. N is the number of observation, k is the number of variables, independent variables. Y is known to us, known to you, x is known to you, b is known to you. So y minus x beta, x with y minus x b is simply your residuals. So you are simply trying to find out the sum of square due to residuals, right? Y minus x b transpose y minus x b. So now this will also give you here the value. And just for your information, although here in the case of multivariate, I cannot create the picture in this multivariate setup, but this beta has been obtained exactly on the same line as we had obtained the beta 0 and beta 1 in the case of simple linear regression model, right? So, but now my trouble is that I cannot create such a picture in the such a k-dimensional space. That was the reason that I had first considered the univariate regression model, where I can show you all the things clearly, and you can also see them with your own eyes, right? Right. So now onwards, we will simply assume that X is going to be a full column rank matrix. Because if you don't assume is, this B cannot be found. And one thing I can share with you, that this B, what you have obtained here, this X transpose X whole inverse X transpose Y, this is a very good estimator. Means it has all the nice statistical properties, but they will be valid only when these assumptions will remain valid. If these assumptions are not valid, then this B is not a good thing. Right. For example, you always say that suppose if somebody wants to cook a good cake, so the cake is going to be good if the ingredients of the cakes are good and the person is assumed to know how to bake the cake. So that is the same story here also, that once these basic assumptions are satisfied, only then this B is going to give you a very good value. And the reason that why sometimes you will get bad results, that is because of this, because one or say more than one assumptions are getting violated. And that is exactly what we do, that when we try to teach here the course on regression analysis, we try to teach all these things, that what is really going to happen when we have these different types of violations. So that is why now in this lecture, I'm going to concentrate on this ordinary least square estimator. And this is also the maximum likelihood estimator of beta. So in this case, the fitted line or the fitted regression model can be obtained. Just try to consider the model y equal to x beta plus epsilon and try to replace beta by b. And then the fitted values means whatever values you have taken for x1, x2, xk for obtaining the value of y1, y2, yn, simply try to take those values of x1, x2, xk and substitute them in the fitted model, try to obtain the value of y's, and they are going to be called as fitted values. They are going to be indicated by y hat. Right, so y hat is simply your here xb, where x is a given to us. And in case if you try to take the difference between the value which you are going to observe and which you are going to estimate from the model. That is the value of y which you observe and the value of y that you obtain from the model for the same given value of x. This difference is called as residual. So now this y difference y hat, that is the difference, means you can take a y minus y hat or say y hat minus y. That doesn't make any difference. Right, because the way we are going to use it, we are always going to square it. And this is the same thing that we had shown you in the means picture, but in the case of simple linear regression model. Right, okay, so now I try to take up this earlier example and try to show you one by one. Is in this output, there are many components. I will try to take one concept, I will try to show you the outcome, and then I will try to give you another concept, and then I will show you the outcome. So up to now, if you try to recall what we have done, we simply have found the value of beta 1, beta 2, beta p, and sigma square. So now if you try to see here, there is a, means I'm just giving you here the formula that how I have computed. There is a command here, lm in the software R, that's the free software. So I have used that software, and then I try to use it on this data. And then you can see here that I have entered the data and then I have obtained the model. But before that, it is very important for you that earlier when you consider the simple linear regression model, then you created a scatter plot. You plot x and y on the two-dimensional plot, and you saw that there is a trend in the observed values of y with respect to x or not. Right. Now, what to do in the case of multiple linear regression model? That's a very big issue. Because in the multiple linear regression model, you just cannot see anything. So one option is that we try to create this matrix plot, as you can see on the screen. Matrix plot is very simple thing. You just try to create all the scatter plots and try to put them just like here a matrix, so that you can see the behavior of all x1, x2, xk with respect to y. Otherwise, you will have to create one scatter plot between y and x1, y and x2, y and x3, and so on. So instead of those things, we have a facility in most of the software. You can create this matrix plot. So it is very simple. It means if you try to see the first row, there are 3 pictures. So these pictures are going to be between y and x1, y and x2, and y and x3. So now obviously you can see here in the second graph where I'm moving my cursor that there is almost a linear trend. There is no issue. In the second case, you can see here that it is going to be a strange type of pattern, but in the y and x3 here, you can see here that there is a sort of linear pattern. So now you can see here the problem here is that you have here a clear-cut increasing linear trend in the case of x1 and x3, but for about x2, you have no idea. But remember one thing, this is univariate analysis, what you are doing. You are trying to see the behavior of y with respect to one variable at a time. But what really you want? You want a joint effect of x1, x2, x3 on y. So that we are unable to find here. Well, in this case, possibly up to 2 dimensions, you can say that, okay, I can create a 3-dimensional plot using the software and possibly can do something, but it is not really so straightforward and simple. And to convince you, you know that in mathematics that if the there are 2 variables x and y which are related, there is a linear combination. And if I try to take a linear combination of all the linear combination, that will also be a linear combination. But you cannot fulfill the vice versa. So that is what we are assuming here, that okay, the relationship between y and x1 is linear, y and x3 is linear, y and x2 is something like, okay, more or less not so good, but still we can take it as a linear. And then beside those things, there will also be some interaction. But interaction effects we are unable to capture so that we can plot them. So that is why we have to depend on this univariate analysis. We have to use our common sense, we have to use our experience, we have to interact with the user, and finally we have to take a call of yes or no, that whether the relationship of y with respect to x1, x2, x3 is linear or not. Right. So in case if that is linear, only then we are going for this regression analysis. So now we have, suppose we assume, yes, the relationship is going to be linear. Now we try to find out this model. So if you try to just use the command of linear regression model on this data, you will get here this type of outcome. Whatever I have written here in blue, that is the outcome of the software. Right. So if you try to see here, means here is the written here is coefficients, then intercept, then x1, then x2, then x3. Now your main job starts here. By looking at this output, how are you going to interpret those values? So now if you remember, your model is like here, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So now it is giving you those values. So the first value, intercept term, is the value of the intercept term 8.769. Then value, the second value here 1.997. This is the value of beta 1 in the model. So that is the regression coefficient which is associated with x1. So this is trying to give us the rate of change in the value of average value of y when there is a unit change in the value of x1. x1 was the number of hours of study. So now you can see here this value is changed from the univariate analysis. And this is happening because now there are more variables and their interaction effect, their joint effect is also present in the data. So now it is saying that if a student studies for 1 hour more, then the marks are going to be increased by 1.99. Say 2 marks are going to be increased. Similarly, x2 here is the number of assignments submitted in the in a week or in a month. So now that is indicating that its value is 3.918. So this is indicating that if a student submit one assignment, then the marks are on an average going to be increased by say nearly 4 marks. And similarly, x3 here is the coefficient related to x3 here is 6.106. This means here what? That x3 is the number of hours of play that you can see here in this data, right? So the number of hours of play, if they are increased by 1 hour, then the marks are going to be increased by 6 numbers. So this is how we try to take the interpretation, and your model becomes a y is equal to 8.769 plus 1.99 x1, 3 plus 3.91 x2 plus 6.10 x3. Right. So this is how you can obtain the model. And if you simply want to obtain here the coefficient, then usually you will have a command here, and you can take out these values. And these values, you see, these are the values of what? These are the value of here x transpose x whole inverse x transpose y. That means in this data, what you have written here, if you try to choose this data y and x, and you try to compute here this expression, which is not difficult, you just write one line expression, it will give you this value. So that is going to give you here the value of b0, b1, b2, b3, which are coming out over here like this. So this is what I wanted to convey you, that is why I'm trying to give you here some mathematical details so that you can understand that's what's really happening, right? Okay. Now you try to obtain the weighted values. Simply try to take the same values of x1, x2, x3 and try to put it here in this model here. Try to choose this x1, x2, x3 and then try to obtain the value of here y. Though these values will be coming out to be here like this, right? So you can see here that here in this data you can see here the values are here. Are here like 180, 116. And if you try to see here, if you try to use those x1, x2, x3 and try to obtain those value, they are coming out to be 180 and 116.02, right? So now can you see here that if you have increased the number of variables, the model is now becoming better. If you remember that in the last lecture when we computed this value, this was very different. Now these values are coming out to be quite closer to the values that you are observing from the model. And if you try to say obtain here, this is the screenshot, the residual vector. That means the difference between the observed and the value that you are trying to find from the model. You can see here, this difference are very small now, 0.00 minus and then minus 0.0. You can see here, and if you try to take this sum, I mean, you can see that, okay, they are very close to zero. So now you can see here that when you are trying to add here some more important variable, how the model is going to change. And now you can interpret it also. And these values are pretty close to zero. So you can see, yes, the linear model can be fitted here, although the true model is only with the God, but at least you are here confident that you have not made a bad choice. Right, and this is here the screenshot of the same thing which I just shown you. Now, I just want to convince you here that why this expression of B, which you have obtained here, this is trying to give you a good value. You see, whenever we are trying to estimate some parameter in statistics, you have to understand this is such a huge population. We are just having a small sample of data, and based on that, we are trying to estimate those values. So we don't know what is going to be the true value. Suppose if I ask you that, can you tell me what is really happening in the some market in say Assam? You cannot know. So we are working, somebody gives you a phone call from say Assam that okay, something has happened, and you believe as if this is happening in the entire state or in the entire country. So this is something like this. So now the simple answer is that when you are trying to find out the value of the unknown parameter of the parameters using the B, then this B is going to give you a good value, because from the statistical point of view, we have some criteria like unbiasedness, variability, etc. So this estimator is an unbiased estimator. Its covariance matrix is given here by like this. Unbiased estimator of sigma square, it is here like this, and the covariance matrix can be estimated by the last quantity. What is the interpretation of this thing? The covariance matrix in B, in the point number 2, this is the covariance matrix of B. Why there is a covariance matrix? If you try to see, you can obtain more than one samples, and every time you try to compute the value of B, that is going to be different. So that means B is also working just like a random variable. And when B is working like a random variable, that means it will also have some variability. So you want to know how much is the variability. But now when you try to find it out, it is sigma square x transpose x whole inverse. X you know, but sigma square you don't know. So you cannot know the value of the variability of this B. Variability means, you know, in application you use the terminology standard error. So standard error is simply the positive square root of the variance. So now the next question is this: can we know the value of sigma square on the basis of given set of data? Answer is yes. And that is what we are trying to obtain in the point number 3. And then we try to substitute this value of sigma square in the point number 2, and we try to find out the value of the covariance matrix of B on the basis of given set of data, which is given here uh, in the point number here 4, right? So now you can see in the point number 4, this sigma square hat is known because that is dependent on only here y, x, and b, and x you know, so you can compute it. But in means anyway, you are not going to compute it, or the software will give you these values. And similarly, when you are trying to find out the estimated value, they are also random. So if you try to find out their covariance matrix, this will be given as in the point number here 5th. And but again, it depends on their sigma square. So if you want to estimate it, you can find out the sigma square hat, and then you try to replace it here, and it will try to give you the estimated covariance matrix. And then In the seventh point, I am writing here the result just for the sake of your information that the ordinary least square estimator of parameter vector, which you have used here, that this is the best linear number estimator of the parameter vector beta. So that means in a simple language, I can say that it is going to give you a very good value. Right. Now, so now you have obtained the model. And then you want to conduct the test of hypothesis. I think uh, Dr. Arun told me that now you have a fair idea about that test of hypothesis. But the question here is how this test of hypothesis is going to be helpful in the case of regression analysis. Well, when you are trying to conduct an experiment to find out a model, you don't know what type of variables you should use here so that you can find here a good model. After you have found the model, there are a couple of questions, whether my model is good or bad. And you also want to know that the variables which you have used, are they good? And then the question comes, what is the meaning of here good? Good means, are they really going to help us in making the model better? Or they are not contributing in making the model better? For example, if I say, that suppose the agriculture production that depends on quantity of fertilizer, say irrigation, rainfall, etc. But now if you try to add here a variable, number of people in US, number of people in different country like US, Germany, etc. Is it really going to affect the yield of the crop? Or if you try to see that the yield is going to be dependent on the, say, the number of people studying or staying in the neighboring state, well, I don't expect. If there is some very minor effect, that is going to be very small and we will not be bothered about those things. So how to know that which of the variable is really going to help us and which of the variables is really not going to help us on the basis of steps? That is our objective. Right. So these things can be answered by the test of hypothesis. For example, if you want to test your null hypothesis H naught beta j equal to 0 versus H1, the alternative that beta j is not equal to 0. So when you are trying to say here beta j is equal to 0, if you simply trying to understand what is the meaning of this, beta j is the regression coefficient with the jth variable. And this is trying to measure the rate of change in the average value of y with a unit change in the value of xj. Now you are saying that beta j is equal to 0. That means the change in the average response is going to be nearly 0 when you are trying to change the independent variable. So how can you interpret it? Yes, in my opinion, I am simply trying to rephrase my sentence that, okay, this variable is not important. Right. So that is how we are going to interpret it. So that if H naught beta j equal to 0 is accepted, that means the corresponding variable xj is not so important. So for example, if you try to take care of this model here, y equal to x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus epsilon, and suppose H naught beta 2 equal to 0 is accepted. So that means beta 2 equal to 0 is valid in the population. So that means the corresponding variable of beta 2 is not as significant. So the revised model can be now here x1 beta 1 plus x2 into 0 plus x3 beta 3. So that will become here x1 beta 1 plus x3 beta 3 plus epsilon. So that means now you are trying to remove the variable. Well, there should be only here single plus sign. By mistake, it is only here 2 plus signs. So now you are simply trying to say here that in this case, this x2 is not going to be an important variable. And so you are trying to drop it. So now this is how you can see here that you can choose the important set of data. Right, now the question here is this: how do you test this hypothesis? For them, I'm just simply trying to show you here that we have here a t statistics, which is given by, say, Bj, that is the gth value of the regression coefficient on the sample, from the sample, and divided by standard error of Bj. Standard error of Bj can be obtained from the covariance matrix, which is the ith diagonal element, take its square root. And that is going to follow here the n minus k minus 1 degrees of freedom under H naught. So yeah, so this is how you can compute it. But the main thing is this: I'm not going to compute it. My software is going to compute it, but my objective is this: I should know what I am doing, right? And after that, if you want to take a call, the procedure is very simple. That reject H naught against H1 at alpha level of significance if the p value is smaller than alpha. So reject alpha in case if the means if you try to find out the calculated value of the statistics is more than the tabulated value. So this is how you can actually check. So but if you try to see, this is only a marginal test. Marginal test in the sense you are trying to consider here three variables x1, x2, x3, but you are trying to conduct the test of hypothesis for one variable at a time. That is why this is called as a marginal test. And this type of test is trying to judge the contribution of xj given all other the explanatory variable in the model are remain the fixed. For example, here when I am trying to conduct here a test of hypothesis for h naught beta equal to 0, I'm not trying to touch the beta 1 and beta 3. So I'm trying to take here only one value at a time. So now I try to do this thing on the given set of data. And for that, I have here a command. And in the software, you will get now here like this one. Right. So now if you just try to observe this outcome, what is this trying to give you here? Let us try to understand one by one. Right. So this is the screenshot. Now, if you try to say, I will just try to take the small subsections of this outcome, and then I will try to show you here one by one. So first, I try to consider this part here, which I am highlighting in the this red, say, rectangle. Now you can see here what it is trying to give you. I will go extremely slow, and you just try to concentrate on my this mouse control. You can see here, first column here is intercept, then x1, then x2, then x3. And the second column here is estimate. So estimate here is trying to intercept is 8.76, x1 1.9, x2 3.9, and x3 6.1. So these are the estimates of actually of regression parameter. That means they are the value of B0, B1, B2, and B3. So the first value 8.7 is the value of B0. Second value here is 1.9. That is B1, then B2, then B3. So the model is now going to be 8.7 plus 1.9 x1 plus 3.9 x2 plus 6.1 x3. Now you come to third column here, that is standard error. If you try to see these four values, these are trying to give you the standard errors of the estimated value of the four regression coefficients, beta 0, beta 1, beta 2, and beta 3. So 1.03 here, this is the standard error of the intercept term. The next value 0.03 is the standard error of the estimate of beta 1, that is the standard error of B1, and similarly third value 0.16 is the standard error of B2, and the last value here is the standard error of B3. So now if you try to see this standard error, how they are coming here, they are coming from this expression, this one, which is on the here fourth term, that you try to find out this covariance matrix and try to consider their diagonal terms, right? Now, if you come here on here, this fourth part here, this is here t value. So if you try to see here, t value is trying to give you here this, the test of hypothesis, which is related to this test of hypothesis, t is equal to bj upon standard error of bj. So now if you try to just consider here this uh, fourth column here, I try to give you here in a more detailed way. So if you try to just see the rectangle inside the rectangle, you can see here the t value here is 8.50. So that means if you try to compute this quantity, t is equal to b0 upon standard error of b0, you substitute all this value, this will come out to be here 8.5, and this is going to follow here a t distribution. But anyway, in the last column, the p-value here is given to be here 2.47 into 10 to the power of minus 7. So this is very small. It is smaller than alpha. So we can see here that we are not going to accept the null hypothesis. And so H naught beta 0 equal to 0 is rejected. Right. So that means the intercept term is important. It is contributing in the model. Similarly, if you try to come to the second row corresponding to x1, you can see here this is here 61.850, which is here the value of the t, and then here the p value here is 2 into 10 power of minus 16. So once again, it is smaller than alpha. Alpha you are trying to take as 0.05, which is the level of significance, that is 5% level of significance. And then in this case also, the null hypothesis H naught beta 1 equal to 0 is rejected. That means the variable x1, which is related with beta 1, this is an important. And this is contributing in the modeling significantly. So in simple words, I can say that x1 is an important variable. Now we come to the third row here regarding x2. So you can see here the value here is 23.493, which is the value of a t-statistic when we are trying to test the hypothesis S naught beta 2 equal to 0. And this is again the here the p value is 7.9 into 10 power of minus 14, which is much smaller than alpha, which is 0.05, that is 5% level of significance. So in this case also we can say that x2 is an important variable. Right, and similarly, if you come to the last row here, x3, the t value here is 84.40. So that is the value of the t-stats corresponding to H naught beta 3 equal to 0. So this means that the p value here is twice, 2 into 10 power of minus 16, which is again less than 0.05, which is the value of alpha at 5% level of significance. So once again, I can say here that the hypothesis is rejected, and so x3 is an important variable. So now you can see here you conducted your experiment with these three independent variables, and now you can conclude that all the three variables are important variables. So now you expect that your model is going to be good. Okay, now after this, there is another concept in the modeling. Whenever you are trying to find out the values of unknown parameters, here you have found those values at a point. And that is the same thing. Suppose if I ask you how much time do you take from coming from your home to your office, you may say it is about 30 minutes. Do you think that means every time you take only the 30 minutes? No. And the second question, how do you came to this conclusion that the time here is 30 minutes and not less or more? What you have done, you have come to your office couple of times and then you recorded the time and then you try to take the arithmetic mean or some average of those values, and based on that you take this time is going to be nearly, say this here 30 minutes, but definitely this can be 25 minutes also, or it can be 35 minutes also, or in fact it can be any value, for example say between 25 and 35 minutes. So now in this case, if you try to see, you are trying to estimate the unknown values in the form of an interval. So this is actually confidence interval. So when we are trying to know the values of unknown parameters on the basis of the random sample, we have two options. We can find out those values at a point or in the form of an interval. So when we are trying to find those values in the means at a point, that is called as a point estimator. And when we are trying to find it in the form of an interval, this is the interval estimator. And the ordinary least square estimator that we have found, that is actually a point estimator. Why? Because you are trying to find out the values at point. The value of this beta 0, beta 1, beta 2, that is going to 3.97, 1.98. So these are only the points. So now we consider here the confidence interval for this beta Js. Okay, so right. Well, we have some methodology in statistics by which we try to find out these confidence interval, and in the case of beta j, and the confidence interval can be found by this expression. So bj is the value of the ordinary least square estimator, t is the value that we try to obtain from the t table, and then this is the standard error of bj. So with this interval, you also come to know that whether your parameters are really good or bad. Right. So if you really want to find out the confidence interval in the linear regression model, it is very simple. Usually you will see they are going to be the part of the software outcome in many situations. And it is an advantage. This confidence interval and the test of hypothesis, they are also interrelated. That means by looking at the value of the confidence interval, you can also take a call for the test of hypothesis. And the relation is that if the value 0 is contained within the confidence limits, that means the H naught beta equal to 0 is accepted. Right. So this is how we try to do here. And now if you want to obtain this confidence interval, well, those formula, I'm not bothered because you are going to use the software. But if you want to obtain it, we have a command here in R is conf int, right? And then write down something. And this label is actually 1 minus alpha, which is alpha is the label of significance of the test of hypothesis. But here this is called as confidence coefficient. So we are 95% confident that our values are going to lie in this interval. So now if you try to see here, these values will come out to be like this: 2.5%, 97.5%. So it is what is trying to do, that it is trying to find out the confidence interval. So the 2.5% of the area on the left hand side and right hand side, that is excluded, and whatever is the value of the value of that curve on the x-axis, that is being indicated here. But anyway, for you, it is as simple as the confidence interval for the intercept term is 6.58 to 10.95. So that means this value is expected to lie in this interval. Similarly, the B1, that is the confidence interval here is 1.92 to 2.06. So the value of B1 is expected to lie between 1.92 and 2.06. And similarly here, the confidence interval for B2 is 3.5 to 4.2. You can see here. So that means here, the value of B2 will lie between 3.5 and 4.27. And similarly here, for here, X3 also, the confidence interval here is 5.95 to 6.25. So that means the value of B3 is expected to lie between 5.95 and 6.25. And you try to see, when you are trying to find all such conclusions, you have only one set of sample data. Based on that, you are trying to take this conclusion which are going to be valid for the entire population. So that is why you have to be careful, and there is always a probability of happening or not happening. So similarly, you can, means if you try to see that how these values have been obtained. So I have given here the expressions by which these values have been obtained. So the moral of the story is that you have to understand how are you going to interpret the confidence interval. And well, software is going to compute it, but I expect that you should know that how they are computed. Okay, and this is here the screenshot, that if you try to do it in R, it will look like, but if you try to take any other software, it will be a similar outcome. Okay, now I come to another aspect, that once you have obtained the model, you have to remember that you are obtaining the model on a very small set of data, but it is going to valid for the entire population. And you have chosen some selected values, selected independent variables. You have conducted the experiment according to your requirement. Now you want to know whether the model is good or bad. So what we try to do, we try to find out the multiple correlation coefficient between y and the group of variable x1, x2, say xk, right? And then we try to square it. So that is called as coefficient of determination. And among users, this is more popularly called as this R square, right? So the value of R square usually describes that how well the sample regression line fits to the observed data. And this is also treated as a measure of goodness of fit of the model. So now, one very important aspect about in this R square. That is, R square is going to valid only if there is an interceptum in the model. Well, this is a fact which I have seen in my experience that many people don't know or they don't want to understand. I don't know. And sometimes even software don't care about these things. The fact is this, because R square is a statistical quantity, and this is based on certain assumptions. And this is going to valid, means the way we are trying to define the R square, that definition is going to remain valid only when there is an interceptum in the model. Well, I didn't knew about that why this is happening. So once a student asked me, then I did some proof, and then I could find yes, if there is no interceptor model, you cannot define the R square in the way what I have defined here, like as R square equal y transpose x into x transpose x whole inverse x transpose y divided by y transpose y, right? So if you try to see here, if you know the value of x and y, you can very easily compute this quantity. And this quantity is simply, you are trying to see that how much the variability this fitted regression model is trying to take with respect to the total variability of the model. So now if you try to see, you have to be very careful here. If you are trying to assume the k independent variable right from the beginning, so now you are saying that one of them is interceptum. So the total number of effective independent variable will become k minus 1. And this value of R square, this lies between 0 and 1. So how to interpret it? Number one, the R square measures the explanatory power of the model, which in turn reflects for the goodness of fit of the model, that how well the model is fitted. And it reflects the model adequacy in the sense that how much is the explanatory power of the explanatory variable is. That means the contribution of explanatory variable or the independent variable which have been chosen only by you, are they really going to indicate whether the model is well fitted or not? Now, how to interpret it? This R square lies between 0 and 1. So if you try to say here R square equals 0, that means this is the poorest fit, and none of the variable is important. And if you try to say here R square equal to 1, that means all the points are exactly lying on the straight line or some p-dimensional figure. So R square equal to 1 indicates that this is the best fit of the model. And similarly, if you try to take any other value of R square between 0 and 1, for example, if I try to take a 0.95, then this indicates that 95% of the variation in Y is being explained by the explanatory variable. Or in simple words, you can say here the model is 95% good, right? So similarly, 0 and 1, that is going to indicate that the model is that much accurate. Now, a very important point at this stage to all those applied workers. Well, I don't know whether I'm right or wrong, but this is what I have seen. I have not seen any research paper where they have used this regression line or regression analysis, and the value of R square of the fitted model is less than 0.98 or 0.99. But now if you try to see, you are trying to say, means I would say that R square equal to 1. That means that God has come from the heaven and God has explained or given you the formula of this process. Now, can you really think that r square equal to 0.98 or 0.99 can really be achieved in practice? Means if you try to say the forecasting model for the weather, if that is r square equal to 0.98 or 0.99, means you should have a second forecasting that what is really going to happen in the next second. Well, we try to improve it as much as I can, but expecting 0.98, 0.99, it's a little bit difficult. But on the other hand, many times I have seen that if you send the paper, the referee will say, okay, your R square is just 0.8. So your model is good. So I cannot expect or accept this paper. Simply write one comment to that referee. Please try to first understand the statistics and then try to comment. And if you don't know, please try to learn it. I'm sure that people are trying to find out the models for the share market and many complicated process. And not even a single time I have seen any R square less than 0.95 or 0.96. But do you think that is it such a simple process? Something wrong is happening. The software is, I'm not doubting on the experimenter that they are reporting a wrong value of R square. But what is really happening, it is something else. Something else is happening because of which the R square here is 0.95 and people are thinking that their model is 95% good. So just be careful here. For example, if you try to see, the R square has a tendency that if more number of explanatory variables are added in the model, this value will always increase. This means what? Even if you are trying to add garbage variables, even then the R square will increase and you'll be very happy. Okay, I have added some variable and my model is getting better and better. Secondly, in case if the constant term is absent, for example, there can be situations where you don't need intercept term. For example, if I take a very simple example, and that is quite popular in the mechanical engineering, for example, if there is some machine whose output depends on the current and voltage, but if you simply try to put the current and voltage to be zero, there is no outcome. So now in this case, the value of y is going to be zero when all the input variables are zero. That means the intercept term is going to be zero. And in this case, you cannot use R square. But still many times people use it and they try to give the value. I don't know how they are trying to give it. Right. So, and when you are trying to say the intercept term is zero, that means the regression line of between y and x is passing to the origin. So now in this case, yes, the question comes here, well, saying that, okay, the R square is not valid, but then the question comes, what is the solution? So some solutions, some ad hoc solutions have been given in the literature, but they are not really dependable, right? But in order to take care of this fact that when we are trying to increase the irrelevant variables also, then even then this R square is going to change. For that, we have defined a modified version of the R square is defined, and that is called as adjusted R square. And that is indicated by R square and then over the bar. And this is defined by this expression here. You don't worry for these things that why and how it has been defined, but then this will actually help us. And when you are trying to add more number of garbage variable, this will increase, but not that much. Right, so let us now try to understand all these things from the software outcome. So we consider here the same data set, and we have here the the value of R square and adjusted R square. Usually software will give actually both of them. So now if you try to look into this outcome, right, you can see here towards the bottom, I have highlighted a rectangle. Here you are trying to it is there multiple R square. That is the value of actually R square. which is here 0.9995. And then adjusted R square, this is 0.9994. So usually you will see that the value of adjusted R square will be a minor, say very little smaller than the value of multiple R squared. Right. So now you can ask me, I'm sure that if you are before me, you will ask me the first question that just now I have given you the interpretation of R squared to 0.995. Now I am also getting here 0.995. How it is possible? The fact is this, I have created that example artificially to show you that how the things are working in the linear regression model. So that is why this is coming out to be so high. Otherwise, in practice, it is very difficult to achieve. That is my very honest answer. Right, so you can see here this multiple R square and adjusted R square, they are given here, okay? And you can see here, for example, this multiple R square is coming obtained by this expression, the R square equal to SS regression upon SS total, which is the same value which you have given here, right? This is the same thing here. And this R bar square, this is obtained by this expression. So now you can see at least this expression, how you are going to obtain it, right? And yeah, this is how here the solution. So now you see here, this is the screenshot which I had shown you in the beginning. And now you have to look into this, and we try to understand whether we have understood all the outcomes of this outcome of this software outcome or not. So let us try to come line by line. So first line here is summary, that is the command. Then you have a call. This is the software means what command I have used. Now, after this, you see here the first line here, residuals. Now do you understand what is residuals? Yes, that is the difference between the observed and the estimated value of y. Now, because this is a summary command, you can always find out the values of residuals also, and in some case they are the part of the total outcome, but it depends what you want. So if you try to see here that it is trying to write down here minimum 1Q, median 3Q, maximum. Now, what is this trying to do? That it is trying to compute all the residuals. For example, in this case, we have 20 observations, so we have 20 residuals, and it is trying to find out the minimum value of those residuals, maximum value, first quartile, third quartile, and median, that is the second quartile of those values. So from this, you can have an idea that how is the spread of this random errors, because random errors are across the line and lower side of the line, and they are random. So this will give you a close idea. For example, if you see here median is the median middle value. So you can, in some sense, you can compare it with the, say, the mean of those random errors which are obtained on the basis of given set of data as residuals. This is 0.09. That means, okay, it is close to zero. It's not bad. And if you try to see here, the minimum value is -2 and maximum value is 1.4. It's not bad. Means, well, randomness is going to be there. The fact is this, if there is no randomness possibility, as a mechanical engineer, you will get your salary, but my salary is going to be stopped from the moment there is no randomness in the nature. Right, okay, so now you have understood. So this will give you some idea about that's how this random error is behaving. Now, after this, you can see here, it is here coefficients. After that, if you try to see this estimate, standard error, t value, and probability that greater than absolute value of t, which is actually here p value. So now you can see here the first column here is interceptum x1, x2, x3. So this estimate, they are the ordinary least square estimators which you have just obtained through the expression x transpose x whole inverse x transpose y. Okay. And then you have the standard errors. That means you have obtained the estimated covariance matrix, then try to consider the diagonal terms, and these are the standard errors, that mean the positive square roots of those diagonal terms. And then you have here t values. So they are the t values corresponding to the null hypothesis S naught beta j equal to 0. So all these t values are something like S naught. They are trying to test S naught beta 1 equal to 0, S naught beta 2 equal to 0, S naught beta 3 equal to 0, S naught beta 4 equal to 0, and their corresponding p values, which are going to help us in taking the call whether my hypothesis is going to be accepted or not. They are also given here. And now you can see here there are some stars which are indicating here that they are the different level of significance, means the value of alpha. You say 1% level of significance, 5% level of significance. So that's because it is based on computation. So software is trying to give you here all means different possible values of alpha. Then you have here residual standard error, which is here 0.922. And so this is the value of here, see here, sigma square hat, right? Means whatever is the random variation, that is the estimate of that variation and taking its square root, because standard error is defined as the positive square root of the variance. So, and then it has got 16 degrees of freedom, because you have seen that because we are based on this decision on the chi-square distribution. So it is trying to say that, okay, there are n minus k degrees of freedom. So 20 is the number of observation and k is the number of total variables. So this is n minus 4, which is 16. Then second last line, this is multiple r squared, which is here 0.995. That means this is the value of r square. Then we have the adjusted r square 0.994, and then here last is here is the F statistics, right? So F statistics is actually about the analysis of variance, right? So analysis of variance is simply the test of hypothesis for testing the equality of all the slope parameters. For example, you are considering here three independent variables, x1, x2, x3, corresponding to which you have here three parameters, beta 1, beta 2, beta 3. So if you want to test the hypothesis beta 3 is equal to 0, then this is that test of hypothesis. So once again, you can see here that p-value is coming out to be at 2.2 into the 10 power of minus 16. So the S naught is not accepted. That means yes, beta 1, beta 2, beta 3 are not accepted. They have got different effects and they are not equal to 0. Well, I have not included this analysis of variance part because I know that it will be too heavy for you to have this so many topics at the same time, but it is just a test of hypothesis, nothing more than that. So now you can see here that in this software outcome, you know each and everything. And now I have taken here a very particular software outcome from the R software, because that's a free software, and I always say that okay, try to purchase the software, and if you cannot, try to use the free software. That will give you the similar outcome. There is no problem of any, say, this copyright, etc., etc. There are no legal issues. So I have used this thing here, and I have given you here the analysis under very say nice assumptions, but in practice these assumptions may be violated. Sometimes the variance will not remain the same, sometimes they are going to be miscorrelated. So when the variance does not remain the same, then it is called as problem of heteroscedasticity. And then in that case, instead of using the ordinary least square estimation, we use the generalized least square estimation. That gives you a better outcome. And similarly, when these random errors are not independent, they are correlated, then this is the problem of autocorrelation. And in that case, usually the observations are correlated. And then, for example, you have heard about time series analysis. Those types of things comes into picture. When rank of X is not the full column rank, it is less than that, then we have the problem of multi-collinearity. The multicollinearity problem is like that, for which we have not got any good solutions up to now. The one of the good solution is given by the ridge regression estimation. And then, yeah, so we have all these issues that we try to teach and learn in the case of regression analysis. And then the more problematic issue comes in the regression analysis when you are really dealing with the real life situation, that these assumptions may be violated in a way that more than one assumptions are getting violated at the same time. Right. So, and the type of solutions what we have in regression analysis, they are trying to deal one problem at a time. So some minor developments have been done, but not much. So what really happens means as a when I try to teach this course, then at the end I try to give an example which was given to me by my teacher, and I will say the same thing to you, that when we are trying to work with the real data, and when we are trying to work with this regression analysis, that means we want to fit here a very good model. The data may have different types of these problems. And now how to solve them at the same time is a situation like if somebody has met with an accident, and suppose there are fractures in hands, legs, heads, there is some internal injury also, internal bleeding also, and that person is brought toward the doctor. Now, how the doctor is going to start? Should the doctor first try to repair the fracture part, or stop the internal bleeding, or tries to first repair the eyes? That is the situation which a doctor has to take on the basis of the given set of data on the given condition. So that is the similar situation to us when we are trying to deal with these types of condition, that all these problems will be coming at the same time, but then we have to see that how we are going to handle them. One option is that in most of the cases we have to handle them one by one, right? So we will try to take means if you ask me, my approach is, okay, you try to see which is the most serious problem, and then you try to first compare first try to solve it, and then once you have solved the most difficult problem, then you try to come to the second one, then you try to solve it. Something will happen, try to take care of the first two problems, and this is how we will move forward. And then we will try to finally get a good solution. It is possible that there may be some violation. We have to make some compromises. For example, we have assumed several assumptions like as normality, etc. And in regression analysis, we have got some statistical tool which are based on some say and we have some graphical tools also, so that we can verify whether these assumptions are going to be valid or not. So now my ultimate final message to you all will be that whenever the data comes, try to first make all such tests. Try to see whether those assumptions are valid or not. Just like if somebody has to be operated, the doctor always tries to check the blood pressure, blood sugar, etc. And finally, when everything is in control, only then the operation is made. So similarly, whenever the data comes, at least I try to give some time and try to understand what are the basic assumptions needed. Because first I have to decide whether regression is going to be applied over there or not. Once I say yes, then I try to check for all the assumption. And then after that, once I am satisfied, I have some idea, well, this is not going to be valid, or this is going to be not valid for 100% or so, we try to make some transformations also, so that those assumptions are met. And then when the data is ready for the application of linear regression analysis, then only we try to conduct this analysis. Right. So I hope I have completed my lecture and I would like to stop here. Now, I think in the last lecture also we could not had an opportunity. So now I thought that, okay, and I know that beyond this thing, Miss Audience cannot understand even this was much actually.
Yeah. So, dear participants, you are now, the sir is open for taking up some questions. So you may unmute and you can ask the questions if any. This is a very good opportunity. So please, I request the participants to make use of this opportunity and ask questions if you have. So in the meantime, sir, can I have one doubt?
Wait. First, I will try to address now your question that you had asked me towards the end. Now you see, now you have here R square.
Yes, sir.
So what you can do that you can add your variables in the model, and after addition of every variable, try to look into your R square.
Okay.
R square will be increasing, but then you have to use your own common sense and try to see whether this variable is really going to affect your outcome or not.
Okay.
And then you have to also see the variability part also, that the variability should not be violated and nothing is entering. And sometimes even we try to make the transformation. If something wrong is happening, for example, I can say assume that okay, so let x square be equal to say x1. So the whatever are the observation, we try to square it, and then I try to put it there as a one. For example, if there is a lot of variability in the variable, for example, I remember there was a data on the income. The income was going from 100 rupees to 5 lakhs rupees. The variability was becoming too much. So I made a one transformation that I took a log transformation. So the log of the values have less variability. So my Y was controlled. And then after doing all this hodgepodge, here and there, jumping like a monkey, finally you will have a good model. So that is what I was trying to tell you towards the end. Yes. And now you can ask.
Yes, sir. Normally, even in the design expert, we or any other packages that we use, it will suggest or it will propose for these transformations. So it says this lambda transformation, and it proposes to go for log or more transformations, and it will even mention how much to be transformed.
Yes.
When we do the transformations, like you
Yes.
said, sir, the R square and adjacent R squares will be, now well fit.
Better.
Yes, sir.
Yes.
But my doubt is about the predicted R square, sir. Even in the general,
Ah,
they even mention about the predicted R square.
yes.
So if you can throw some light on the
Yeah. You see, one thing what you have to always keep in mind, and that's a very common mistake when we are trying to do the forecasting. For the forecasting, first we have to hit the model. We have to obtain the model. Based on that, we have to do the forecasting. So similarly, if I try to take a very realistic example, suppose you have the data uh, from say 2000 to 2020 or say 2019. You try to hit a model. And if you try to forecast what is going to happen in 2021, you are trying to assume that the trend, what was there between 2000 to 2020, it was like this. So this trend is going to continue. So you want to know what is the value in that 2021. Now, if you try to see, 2020 was a horrible year. Everything got changed. Right, the same talk which you are which I am giving here, possibly in the last year, if you had asked me, I have to travel to your institute, and possibly I will say I don't have time to spend 3 days of travel and then to give 4 hours of lecture. Possibly I would not had uh, uh, it was difficult, and then it's an expensive affair also. Right, so but now you see it was so convenient. Right. So now the thing is this 2020 is going to play a very important role. And now you tell me whether the trend that was there between 2000 to 2020, is that really going to continue after this?
No.
No. But people don't understand this thing, and they try to use the R square prediction for forecasting in 2021, which will never meet. So R square prediction will work only when R square is good.
Okay.
So, for example, if you try to take the data between 2020 and say 2017, try to fit a model, try to make a forecasting for 2018-19, that will actually work. And in that case, you will see that R square and R square prediction, they will will be some different, but not much.
So for any model that we have prepared right now, so in order to get that confidence and use it for further processing, like you rightly said, whether you want to eat it raw or cook it.
Yeah.
So this model to confirm that, yes, this is correct now. If my R square value is close to 1, that is 1 point, adjacent R square should be closer to R square. And
It will always be actually close to R square. That there will be a difference. What I have seen in real life, that will be in the third place of the decimal only.
okay, and adjacent R square, and they even say about the predicted R square that it should not deviate more than 0.2.
Actually, you see, if there is a very serious drawback in your model, only then this is going to happen.
Okay, but generally, even the predicted R square will be closer to.
Yes.
Okay.
Means if everything is good, it is the same thing. If I have to cook, say this milk pudding, I take some milk, I take some rice, I take some cashew nuts, I take some almonds, I take some dry fruits, I put some sugar. Whatever I do, this is going to be good. The problem comes only when I try to put some black pepper into it.
Yes, sir.
That is as simple as that.
Okay. Thank you, sir. Any other question from the participant side, please?
I hope no questions. Yeah, that's good. I'm so tired. Right then, all done then?
Okay, sir. Thank you very much, sir. It was very kind of you for accepting the request and delivering 2 sessions constantly. And then you have given a very simple, easy to understand examples. And I really thank you for accepting the invitation. And we get to interact and get to know about the fundamentals, because normally we generally miss these fundamental concepts which only statisticals can address. And I'm really happy that you have accepted and we were able to see the sessions. And I really thank again for writing those 2 books, sir, which are wonderful. I really
That was
enjoyed.
my bread and butter.
Sir.
That was my bread and butter.
Oh, nice. I really enjoyed reading those 2 books.
Roklo.
Thank you very much, sir. Thank you.
Right.
Thank you, sir. Thank you very much.